why process modeling is not just placing blocks on the flow diagram, and what do you need to know in order to develop reliable and accurate process models. Why I'm talking about this? Well, many cases you hear that process modeling is just placing blocks on the flow diagram because you've got process design tools, process simulators, where you've got a library of models, available models, unit operations that you can basically place on the flow diagram and then connect with each other. Well, it is the case, you can do that, but in order to develop reliable models and make informed decisions or recommendations, you of course need to understand the thermodynamics behind that process, at least thermodynamics, right? There are other aspects as well. So let me give you an example that I usually give to my students when I start with Aspen Plus. Okay, so I usually do the case study in Aspen Plus where they understand what sort of unit operations are there, what sort of interconnectivity is required, and they need to understand the main process, right? But then we might have the example using equation-oriented process modeling tools like engineering equation solver. So I like engineering equation solver, EES, in particular, mostly because it contains the database of all the properties as well for the most commonly used liquids, fluids in general, right? So that's why I do enjoy it, do like to use it, because I don't have to search for data elsewhere. So in principle, EES, or engineering equation solver, is a very nice piece of kit where you can code the equations in. So for example, in this case, in the gas turbine case, we've got three transformations. We've got compression of gas, we've got heat transfer. In this case, we have externally driven gas turbine, which is the heat addition between point 2 and 3 happens via heat exchanger. And then we have the expansion or transformation of the gas energy or heat pressure energy into the mechanical energy of the shaft, right? So of course the shaft connected with the compressor, so part of the energy generated in the turbine is used to drive the compressor. Sorry. So in order to calculate this, in order to represent this using the thermodynamics, we do have to talk about enthalpy, entropy. We have to specify the isentropic efficiency calculations for the specific piece of equipment. So this is what we did here. This is the example available in EASE, but this is basically very useful because you can see that you have to specify the inlet state, you specify the pressure ratio of the compressor, right? So you do have to time that in. Efficiency of the compressor, so that's the isentropic efficiency of the compressor over here. The work of the compressor, which is basically the difference between the enthalpies at the inlet and outlet of the compressor, and then the heat addition, again the difference between the outlet and inlet for the heat exchanger in this case. Well, you can see that, looking at the thermodynamics, it can get quite complex. This is a simple example, but it can get quite complex. So you would obviously reuse some of these definitions as the unit blocks, as the unit operations. So when you initially start developing your equation-based unit operations, you would save them as a single unit operation and then refer back to this. So this is basically what process modeling tools do, right? You've got a set of unit operations, you can link them back together, but you do need to understand what they do. You do need to understand how they operate, what are the correlations behind compressors, heat exchangers, reactors, and so on, so that you can make informed decisions in order to analyze this and design the process. So just to give you an example, again, you can basically just verify. So basically, once you put those equations in, the EEs will work exactly the same way as Aspen Plus, right? So you can change the efficiency of that compressor, and it will basically be, so this will be reflected in your results. So your efficiency will go higher because you have higher efficiency of the compressor. If we reduce that efficiency to, say, 65%, which is very bad compressor, very deteriorated compressor, and you run the results, you would basically see that the overall efficiency of the process decreased. So this is something that you can also do using a generic equation solver.